Hello, this is Michael Kogan. I am doing problem 5, chapters 27 through 28 for my exam. Uh, this whole exam is pretty much just on magnetism and different forms of it. So this section specifically is mainly on wires, I believe, and their effect on, such things. So we'll start off with problem A. Start by lifting off the variables. So the question is, how much current must a long straight wire carry in order for the magnetic field that it produces, 1.4 centimeters from the central axis of the wire, to have magnitude 3.2 times 10 to the negative 5 Tesla? Okay, so let's first write down our variables. We got length is equal to 1.4 centimeters. Okay, and the magnetic field magnitude is 3.2 times 10 to the negative 5 Tesla. Okay, so to find I, we'll need an equation. And luckily for us, this is already an equation that we have. Uh, find I, we need the equation B2, or sorry, B times 2 pi times R times mu naught. So the permutation constant. So, and that will equal, so let's write this out, 2 pi times 0.014 times the magnetic field, 3.2 times 10 to the negative 5th Tesla, divided by mu, so 4 pi times 10 to the negative 7, and that will equal, check, 2 times pi times 0.014, which is the length of the wire, times 3.2 times 10 to the negative 5 divided by 4 times pi times 10 to the negative 7, 2.24 amps. Okay. And moving on to part B, we will need, actually, I believe this section's variables are for B through D. So we'll just write down B dash D. And we'll start off by reading the question, right? Two long straight conducting wires are both perpendicular to the XY plane. Wire 1 passes through point 0, x equals 0, y equals 1 centimeters, z equals 0. It carries current 1 amp in the positive z direction. Wire 2 passes to the point opposite of that. It carries current 4 amps, also in the positive z direction. Find the net magnetic field due to both wires at x equals 0, y equals z, and z equals, or x equals 0, etc. So first we'll write down our constants, right? So I1, right, the first wire has 1 amp. R1, so that'll be our first location, has the vector 0, 1, 0. And B is going in the positive direction. So we'll write down just K here. So remember it's in the Z direction. I2 has 4 amps, also K direction, right? And R2 equals 0, negative 1, 0. Okay, so with this, we can draw a little diagram. So we have one up here, one down here, right? And let's remember our right hand rule, right? So since the magnetic field is going up, it curls this way. So here it will have this direction. Here it will have this direction. So this one's pushing it forward, this other one's pushing it backwards. So we can use, if we want to find the amount of force applied to it at the origin, we'll do to find B, the vector B, we use, or I should clarify, very important to clarify this, at r vector equals 0, right? So at the 0 vector where x, y, and z are all 0, we use the summation rule. What is the summation rule? It is sigma b equals b1 plus b2 plus dot 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 all the way to bn, right? Uh, yeah, sure, whatever. So to do that, we'll have to set up the equation. The b vector equals mu times I1 divided by 2 pi of R1 plus mu naught of I2 divided by 2 pi of R2. All right. And remember, we're getting distance here, right? So we'll set up this equation with just the magnitude of the distance. So I'll actually clarify that. I'll put down magnitude brackets here. Okay. So, but we need to preserve the sign for this one. So we'll actually set this up right off the bat as negative. And this will be for the first vector, first part of the vector, so in the x direction. Because let's remember, it's going upwards. Vector field is pushing it this way in general. It's only pushing it this way or this way, right? So it's only affecting on the x direction. Sorry, I don't know why I use this rule. But so we'll do minus since the second one is pushing in the opposite direction and this one's pushing in the positive direction. So then we will get 2 times 10 to the negative 7, right? Canceling out the pi and the 2. So that just leaves it to 2 times 10 to the negative 7 times 1 divided by 0.01 minus, again, 2 times 10 to the negative 7. That's usually a good number to remember for this stuff. 4 divided by 0.01. And that will equal that will equal 6 times 10 to the negative 5. 5 Tesla, and that will be in the I direction. And nothing else should be changed. Since no forces are pushing it up or down, since it's perfectly right at the center. Okay, for problem C. It says find the net magnetic field due to both wires at y equals 2 centimeters. Still x0, z0. So we're not going really to size. We're just going up and down. Okay. To find the b vector at equals, and this is at 2 centimeters, so 0 point, or 2 centimeter, 0. We gotta use the same equation, same one, same uh, b vector equals mu I1 divided by 2 pi r1, and we'll just do a plus sign for now, of mu 0 I2 2 pi r2. Okay, now let's look at this field. Now it's up here, right? So now both are pushing in the negative direction. So we'll just leave this as well. So we have two options here. We could do minus and put this one as a negative, or we can just remember its direction. I personally usually just remember its direction. Uh, it's a little bit more intuitive to me, especially when we're dealing with more simplified math like this, where we kind of lose negative signs as we go. Uh, but it's important to remember it's negative. It's headed this way. So, okay. And again, it'll just be in the x direction, not side to side, just up. Uh, so, to plug in these values, we will have to do 2 times 10 to the negative 7 times 1 divided by now, again, 0.01. And yet again, if you do just take the values without taking the magnitude of the vectors, this would be negative since it's going up. It's, well, since the point that we're looking at has to go down to reach it. And this one would also be negative. Once I get there, hold on. It'd be going up. It'd be 3 away in the negative y direction. And then when you multiply that all out, you'll get negative 4.67 times 10 to the negative 5. And then for the final part on here, oh, yeah. Also, very important to remember, always label what vector you're talking about, because this can mean anything. It can literally mean any value in the I direction, or and then you'd have to take it out of its vector form. But for our sakes, the b vector in the I direction is 4, or negative 4 times 6, 7 times 10 to the negative 5. You can test that by its points backwards, and that makes sense for our diagram. Now for d, to find the vector b at vector r equals 0, negative 2 centimeters. Okay. We can use the same equation, right? So we'll set that up again. Same exact thing. And then we'll evaluate what direction we need to analyze this in. Afterwards, 2 pi r1 plus mu naught of I2 over 2 pi r2. Okay, so now that we're down here, right? See, this line goes this way, pushes it this way, and this one also pushes it that way. Okay, so now we know we're getting a positive x direction, since all forces are forcing this thing to go this way when we're down here. It is important to remember too that these are both positive z. Otherwise, if one of them was negative, then at the center they'd be both pushing in the same direction. But it's not, since they're both positive. They go in the same direction. So when you hit in between them like that, it will cancel each other out if they had the same ampage. So now that we know that these are both positive, so then we just plug in our values, right? So that we have 2 times 10 to the negative 7 times 1 divided by 0.03, since they just swapped, and 2 times 10 to the negative 7 times 4, 0.01. Since it has to move up in the positive direction for each. For this, it will be 2 times 10 to the negative. I don't know why he cleared it out again. This time, 0.03 plus 2 times 10 So -7. I'm already predicting in my head, by the way, at this point, that it will just be oh, sorry, my bad. Okay. My prediction was wrong, so we're just going to ignore that. It is 8.67 times 10 to the -5 Tesla in the positive I direction. Okay. Remember, I is this way, Z is up, or K is up, and J is the other way. Okay. So now that we have that, we can move on to E through F. As the next set of variables we are given. All right, and let's see what we have there. The question states a long straight wire straight conducting wire carries a current of 2 amps. The second identical wire is parallel to the first, separated from it by 4 centimeters. Magnetic field at a point halfway between the two wires has magnitude 5.5 times 10 to the -5 Tesla. What is the current in the second wire if its direction is the same as in the first wire? Okay, so we're given the magnetic field, we're given the ampage of one wire, giving the direction for both, and we're giving the distance between. Okay, so first let's start off with labeling these. Okay. I1 equals 2 amps. R, and we'll put R1-2 since it's just the distance. It's 4 centimeters. And the magnitude of the magnetic field is 5.5 times 10 to the -5. 5.5 times 10 to the -5. And that's in Tesla. What is the current in the second wire? Okay. So to find I2, at I2 being greater than 0, obviously, for it being positive, since we're measuring that distance. So let me make sure to write this down. And I'll write down I2 equals question mark, but it's also in the K vector. So I can write down X or like a normal variable. I just like putting down a question mark to remember that is what we're looking for. So let's write out a question. E to find. I just had a heart attack. I thought my mic would be muted this entire time. Okay. To find I2 at I2 being greater than 0, right? So K being positive, use B vector equals negative mu I 2 pi R1 plus same thing mu I2 over 2 pi dt. I don't know why I put down t there. My bad. I guess too used to Calc 1 still for some reason. Okay, then we can solve that out as -2 times 10 to the -7 times 2 divided by 0.02 plus 2 times 10 to the -7 times I2 divided by 0.02. And when you multiply that out, you will get 7.5 amps. All right. For F, so here, let me write that over here again because I kind of ran out of room there. Kind of bad habit to do. So for I2 being positive, so remember that's traveling in the K direction. Now for F, we're looking for it if K is negative. So to find I2 at I2 is less than 0, we use the exact same equation, except for everything's positive. So mu I 2 pi r plus mu or 2 or 1 divided by 2 pi r, and that goes to 2 times 10 to the negative 7 times 2 divided by 0.02 plus 2 times 2, or 10 to the negative 7 times I2, 0.02, and that will go to 3.5 amps. All right. And then for part G through H, almost done. For parts G through H, the question is two straight parallel superconducting wires are 0.9 meters apart. Both wires are oriented straight up and down. One wire carries a current of 1.3 times 10 to the 4 amps upward and experiences a magnetic force per unit length of 95.0 newtons per meter that attracts it to the other wire. What are the magnitude of the current in the other wire? Okay, so first let's write down our variables. R equals 0.9 meters, right? I1 equals 1.3 times 10 to the fourth amps. And force per length, or F over L is how I just read it, was 95 newtons per meter. Okay. And then that's a pretty simple equation after that, right? So, G, I'll write down to find I. What's right, is it? Okay, I2. Let's write down I2. I don't know why I wrote down I prime. Oh, sorry, because I got confused because, yeah, the formula that I use. But to do this, we use F over L equals mu naught of I1, I2, it's usually written as I prime, sorry about that, 2 pi times R. And then we can transform that, right? We have, or to get the actual formula, we can do F over L times 2 pi R divided by mu naught I1 equals I prime, or I2, sorry. And then we can transform that as 95 times 0.09 divided by 1.3 times 10 to the 4 times 2 times 10 to the negative 7. Then we'll work that out. You get 3.29 times 10 to the 4th amps. And then for H, the question says, what are the direction of the current of the wire? So, and we can look at it mathematically, right? It's positive, so it should be upward. But if we look at it mathematically, they're placed 0.9 meters apart. So let's say there's one here. Or sorry, one here. And they're 9 meters apart. They have the same force. Boom. And then, sorry, I don't know why I started drawing out this diagram. It makes more sense when you use the cross product. But we do know, since it's positive, it'll be going upwards. I do apologize for that. All right. Well, that's the whole video. So thank you for watching.